So in this project, we tested how changing the mass of one IOLab cart affects the collision when it's hit by another cart moving at a constant speed. One cart stayed still while the other collided with it each time. We changed the mass of the resting cart from heavy to light to no extra weight, and then the main goal was to see how mass affects the elasticity of the collision. Here we explain the main physics ideas behind our project. Energy and momentum are always conserved overall, but energy can change forms, like turning into heat or sound during a crash. Momentum is equal to mass times velocity, and in inelastic collisions, objects stick together and lose some of that kinetic energy. This slide shows how our experiment connects to something familiar, a car crash. Before the crash, both cars move separately, each with its own momentum. When they collide, they often stick together and move more slowly as one object. The total momentum is conserved, but some of the kinetic energy is lost as heat, sound, or deformation. This slide explains how Newton's second law, F equals ma, connects to our experiment. When the moving cart hits the resting cart, both experience equal and opposite forces that cause changes in speed or acceleration. A bigger force means more acceleration, and a heavier cart changes speed less from the same force. This helps to explain why the heavier cart moved slower after the collision, while the lighter one moved more.
Our research question is about how inelastic/elastic a collision is with different weights. The motivation behind this lab is to better understand how energy and momentum behave during collisions, especially when the collisions are not perfectly elastic. In real life, most collisions lose some kinetic energy as heat, sound, or deformation. So studying inelastic collisions helps us understand these energy transformations. By experimenting with different variables like mass and surface type, we can see how they affect how much energy is conserved or lost. The materials we need are 2 IOLab carts, a meter stick, a 100-gram weight, a 400-gram weight, and an IOLab software. The first step is to connect the IOLab carts we will be using to the software on the computer. We do this by plugging in a USB drive that makes it able to connect both carts via Bluetooth. After this, we must then decide which direction is the relative positive and negative direction for both carts, since this will be needed for when they collide. Once we have finished that, we attach a spring to the cart that will be initiating the collision and a plate to the cart that is at rest. For the distance to be the same between each trial, we use a meter stick so that it stays consistent. The cart that is colliding starts 30 centimeters away. However, since the spring goes off the front of the cart, it makes it 25 centimeters away. Lastly, we put additional mass on top of the cart at rest. After these steps have been completed, we start colliding the carts and gathering the data.
So for our reference frame, we had the 2 carts, obviously, with the one weight on top, and we had the IOLabs oriented so that the left direction was negative, which was the way that cart 2 is traveling, and positive being opposite to the direction of cart 2's travel. And cart 1 is described as B in the calculations, and cart 2 is described as A in the calculations. This slide shows the heavyweight trial and the various measures of initial and final velocity for both carts. We use the coefficient of restitution to calculate inelasticity, and this usually works from a scale of 0 to 1, and the value of 0.636 is a little bit closer to 1, meaning that it's moderately elastic. This is the lightweight velocity versus time graphs, and we found this to be a little bit of an outlier amongst our trials, and we found that this had a value of 0.142 when calculating the coefficient of restitution, and that's something we'll go over potential reasons why in our discussion of our results. For our no-weight trial, this yielded results more expected in the velocity versus time graphs, showing coefficient of restitution roughly around 0.723, which was a decent bit higher than the more inelastic collision of the heavyweight cart. And overall, it shows the trend that we would expect, or that we predicted, of the idea that the heavyweight cart would be the most inelastic and the no-weight cart would be the most elastic. We expected the lightweight cart to be somewhere in between. We used the propagation of error equations regarding multiplication and division, as well as addition and subtraction. So we got the heavy, light, and no-weight trials uncertainty from finding the mean value of the relevant velocities in our IOLabs, and those values are listed there. And we used those in combination with the addition and subtraction propagation of error equations to solve for the heavy, light, and no-weight trials listed on the top section of the calculations portion. And then we use that again in combination with the multiplication and division propagation of error equations to find each corresponding trial's uncertainty. And we found that the no-weight trial tended to be the most uncertain. We found that the error that we likely faced in the previous slide as we discussed uncertainty was likely in trying to keep the motion strictly 1D and avoid that 2D motion of x and y directions as IOLabs bounce off of each other, and trying to keep them in line with each other. And this led us to use springs that made the collision more elastic in itself, as the springs would conserve most of that momentum. Another thing that we struggled with was keeping the velocity relatively constant. We ended up getting around 0.4 to 0.5 in most of our trials, but as well as this would result in different final velocities, as well as like the slight angle that the car would hit the opposing spring at. Like I mentioned while discussing our data and velocity time graphs, we predicted that the heavy collision would be the most inelastic, the light collision to be the moderately elastic, and the no-weight collision to be the most elastic. And our actual results showed mostly that trend outside of trial 2, and the discrepancy in the trend with trial 2 is likely due to the awkward angle that the car might have spring, or the car might have come away at. I mentioned earlier, things that might have been oversimplified in our model was trying to keep the motion 1D. We ignore that the 2D aspects of the cars bouncing, or like how that might complicate our calculations, as well as the overall conservation of momentum. For future improvements, we would probably suggest a set track that
So to wrap up, we found that as the mass of the cart decreases, the collisions become more elastic, while heavier carts lose more energy. Overall, our results matched our predictions and helped us better understand how momentum and energy behave in real-world collisions.